So I think probably a couple of things on this slide. Let me go ahead and get it all up here and then talk about it. One of the things that we've talked about in here is that light and radio waves and gamma rays and X-rays and infrared and ultraviolet, all of those forms of energies all travel at a certain speed called the speed of light. And if an object is 100 light years from us, then it will take 100 years before we see the photons from that object. So if an object is 1 billion years from, 1 billion light years from us, that's at light years as a distance, 1 billion light years from us, then it'll take 1 billion years for that those photons to get to us. So now if we estimate the age of the universe as 13.6, 13.7 billion years, the age of the universe, can you see that if we try to look 13 billion light years from our galaxy or from Earth, can you see where we can see those photons, but when they finally get to us, it took 13 billion years for them to get to us? Now, if we try to look at something, let's go 15. If we try to look at an object that is 15 billion light years from us, can you see where, from our estimation, our universe, the space and time associated with our universe, did not exist 15 billion years ago? So there would be no photons, no stars to emit light or any other sort of energy that long ago. So we kind of run up against a roadblock. It's called our Cosmological Horizon. And so in all directions, we can't see any further than the universe. We cannot see any number of light years further than the universe has been in existence as far as years go. Does that make sense? The other thing I kind of want to show you is this expansion, the expansion of the universe. The fact that it seems like all galaxies are moving away in all directions, not necessarily from a single point. Now I'm going to kind of show you two scenarios. This scenario isn't probably as accurate as the next scenario. So we're going to talk in Unit 5 a little bit about the Big Bang, and we'll talk about a point we call singularity and the fact that actually all matter that's associated with the universe was contained in that single point. And let me go ahead and play it. We'll play it a few times. Okay, the Big Bang. Okay, all matter spread apart. Let me replay it. Okay, now in this scenario, you kind of see the galaxies. Those are galaxies all moving away from each other, moving away from us, and we look like we're kind of at ground zero. Okay. Rather, though, this is probably more to the point, and we're going to talk about, and I'll encourage you to watch extra videos in Unit 5 as well, but we're going to talk about something called inflation, where actually space and time, as I understand it, expanded faster. This is right after the Big Bang, and it just expanded faster than the speed of light. And then after that, we kind of have the fabric of space-time to go ahead and continue expanding there after that. Okay. So notice in this scenario, a little bit of what's different is there is no center. There is no center at this point. Basically, we finally have the fabric of space-time, and that fabric is expanding in all directions. And we're going to actually see and I think I might have mentioned that it's not only expanding in all directions, but its expansion is accelerating. So yeah, there you go. All right. So actually, we kind of talked about this expansion clear back in Unit 1. I don't know if you remember, we had the raisin bread, and basically, which I've never eaten maybe I have eaten raisin bread, but where you have the raisins represent the galaxies, and as the bread bakes and the whole bread, the loaf rises, and all those raisins move apart from each other. Okay. So expanding universe, the raisins are moving apart, the galaxies are moving apart. It's oftentimes, and also been explained with a balloon, where these dots on the outside of the balloon would be the galaxies, and the balloon itself is the expanding universe, and you can see the dots move away from each other. And in this scenario, to me, you kind of have to think of it's after inflation, you kind of have kind of balloon upon balloon upon balloon, and they all expand at the same time. So in that sense, it doesn't necessarily have a surface like you see here. So one of the things that with Hubble, they've been kind of, remember we said we used Hubble to look in a location in the bowl of the Big Dipper where there were no stars. So they're like, hey Hubble, go look over there, there's nothing there. And as Hubble looked farther, it came up with all of these galaxies. Well, if you kind of step back, take a bird's eye view of kind of even the galaxies, what you see in the universe is kind of a homogeneous mixture, or I said pretty, not, it's pretty homogeneous in that it's, the matter is distributed pretty evenly. I know it doesn't seem like it. Maybe on our Earth we think, well, we've got all the matter, but if you bird's eye view back, it looks like the matter is pretty uniformly distributed across the universe. The universe doesn't appear to have any place where perhaps the Big Bang, there's no center of the universe and no edges to the universe. So one of the things that may or may not boggle your mind is this. Since we live in an expanding universe, and what that means is, space, the fabric of space and time is literally expanding. That means that our galaxies are all kind of relocating farther from each other. And so here, this spiral here on the left is the Milky Way, and this over here on the right is a galaxy that can you see this little supernova event? And again, we know we can see these supernovas occur in distant galaxies. So that was 400 million years ago. So fast forward to today, and we know that now there's more of a distance between us and that galaxy. There's more of a distance between us and every galaxy. Okay? So then what happens then to when we finally see that nova event? All right? That nova event occurred clear back here 400 million years ago, right? But if we're finally getting the photons here, I don't know, I didn't say that right, because it wouldn't be 400, the nova didn't occur 400 million years ago. It would have had to have occurred, let's see, less than that or more than that. My point is, when we finally see it, that light was emitted over here, and the galaxy itself has relocated. So instead of like kind of now talking about the galaxy is actually here, even though the nova occurred here, we do talk about something called look-back time instead of where the galaxy really is. I don't know if that makes sense, but it's kind of mind-boggling to me. So we did have a certain distance between us and that galaxy, clear back 400 million years ago. And now this distance, even though we can gauge the distance between us and that supernova event as the galaxy was way back when, actually there's a little bit of play in this particular distance because the galaxy is relocated. Does that make sense? Okay, so don't think about it too hard, but it's like a subtle sort of thing. All right, so the space and time themselves have been expanding ever since the Big Bang. And so, again, if we kind of go back to the balloon and we think of the, let me go ahead and show you this little animation. We have something called cosmological redshift, and it's a consequence of the fabric of space expanding. So I'll go ahead and start this. So as this balloon expands, look at this color that's being emitted in there. So here we have an object emitting radiation, and it's blue. The same object emitting radiation, it's green. radiation. It's yellow, it's orange, it's red. And again, has to do with the fact that space and time, space in particular is the way I think of it, is expanding, so it is actually elongating that energy, giving a longer wavelength. Is that crazy or what?